So let's go ahead and get started on Chapter 4, Probability Distributions. So we're just going to do these first two sections here. We have a random variable for 4.1. Random variable is a variable whose value is determined by the outcome of an experiment. So a variable whose outcome is determined whose value is determined by the outcome. This is value, sorry. Okay, just another vocab word for you guys. Random variable x, just a certain outcome that we're looking at. We have two types of variables, discrete and continuous. Okay, so this is calling back to Chapter 1 for discrete and continuous. I think Chapter 1. And when I look at the homework, there's really just like one question. Yeah, I'm looking at it, so I'll show you guys that. But so you have discrete is just going to be countable values, so there's gaps in between the values, and you're going to see that number of a lot of times. So an example of that would be number of heads obtained in a coin toss. Maybe number of siblings. Let's see what else we have here. Number of lightning strikes. Number of times someone says like in a speech or things like that. Okay. Continuous is going to be any value contained in one or more intervals, so measurable. So length, time, weight. Let's see here. Yeah, length, time, weight. Pricing is going to go into this. Okay. And then those random variables, most of the time we are looking at discrete variables when we're doing probability distributions. Okay. So a probability distribution is going to be a table that lists all the possible values that a variable can assume and then the corresponding probability. So you're putting it into a table. Couple of properties. These will be vocab questions on the test. So the probability of a variable must lie between 0 and 1. So probability is between 0 and 1. And the notation for that is 0 is less than or equal to the probability of x, which is less than or equal to 1. And then the sum of probabilities in a valid probability distribution must equal 1. So just to show you guys an example of something you might see on your homework, you're going to have there's going to be a couple tables here, and you're determining if they're a valid probability distribution. So you'll see like x, p of x. Okay, and let's just say you've got this point x 0, 1, and 2, and then 0.25, 0.5, 0.25. Okay, that's a valid probability distribution because you add those up to 1. Okay, so the sum of these is 1. let's say you have one okay, maybe like this, 0.5, 0.5, 0.1. Okay, well the sum of that is 1.1. So that is not a valid probability distribution. Or if you saw something like this, let's say negative 0.25, 0.75, and 0.5, even though the sum of that is 1, it's not a valid probability distribution because probability has to be between 0 and 1. You can't have a negative probability, okay? So this would be valid. Okay, these two are not valid. Okay, the first one, because the probabilities are more than 1. The second one, even though the sum of the probabilities is 1, you cannot have a negative probability in your distribution. Okay, and then for number 2 over here, the notation, it would just look like this. The sum of p of x equals 1. So both of those have to be true, not one or the other. Both of those have to be true in order for probability distribution to be valid. And then you have a probability mass function is going to be a function that generates probabilities when specific outcomes are input. So that's just an algebra function that's going to give you specific probabilities. Bless you. Oh, it cut it off again. Okay. So let's look at a probability distribution, and sometimes you're going to be given probabilities, and you're going to have to fill in the table. Maybe there's one missing. Sometimes you're going to have to generate them on your own. So we're going to go through this whole thing where we're going to start with, we're going to generate everything on our own, and we'll go backwards here. So according to Pew Research, in 2019, 30% of Americans report that they are almost constantly online. Suppose a random sample of 3 Americans is selected. Let X denote the number of Americans in the sample that report to be almost constantly online. Construct the probability distribution of X. Okay, so when I'm looking at this, let's think about what's happening here. We're selecting 3 people. So you have, I'm missing a thing here. Do you guys have enough rows? Oh, that's weird. Okay. Yeah, you should have 4 rows because you could have the possibility that 0 people say that they're almost constantly online. 1 out of the 3 people say that. 2 out of the 3 people say that, or all 3 say that. Okay, so you have 4 possibilities. For X, the number of people, number of Americans that report to be constantly online. Okay, you have this. You have the probability that someone is online is 30%, so 0.30. Okay, you have the probability that someone is not online. What percent is that? What? So if the probability is 30% that they are online, the probability that they're not online would be 70%. Because remember, the probabilities equal 1. Okay. Now, in order to do the chart, we want to think of all of the possible outcomes that can happen. So this is going to go back to the formula that we had in chapter 3, where the number of possible outcomes is the number of outcomes. So either they're online or not online. So that's 2 outcomes raised to the number of experiments, which here is 3. Okay, because you're selecting 3 people. So 2 to the 3rd is 8. So you have 8 possible outcomes. Okay, now to figure out what those outcomes are, I should have given you a lot more room. I'm going to go to another page and draw a tree diagram for this. Okay, so we can figure out what those outcomes are going to be. Actually, I want this to copy over on the notes, so I think I'm just going to go over here. Okay. So let's think about this. Okay, remember the tree diagram? We can select our first person, and they can either say that they are online or they are not online. So O for online, N for not online. Okay, then your second person, same thing. Online, not online, online, not online. Okay, then your third person, same thing. Online, not online, online, not online, online, not online. But that's it, we're just doing 3. Online, not online. So you have your possibilities. You could have the first person is online. So follow my pen here. First person is online. Second person says they're online. Third person says that. So O, O, O for the first one. The probability of that, remember the probability of being online? 30%. So the probability of that is 0.3 times 0.3 times 0.3. Which is 0.027. Okay, your next probability, online, online, not online. Okay, the math for that would be 0.3 times 0.3 times 0.7 for the not online. So 0.3 times 0.3 times 0.7 0.63. Is it 0.063? Okay, then online, not online, online, so O-N-O. Okay, so that's 0.3. I'm running out of room here. Put it right here. 0.3, 0.7, 0.3. That's going to happen to be the same thing, 0.63. Or 0.63, sorry. Because 0.3 times 0.7 times 0.3, same thing as 0.3 times 0.3 times 0.7. Okay, then you have online, not online, not online. So O-N-N. Okay, so that is going to be 0.3 for online, and then 0.7, 0.7. Okay, so that's going to be good. No, that's 0.3. 0.3 times 0.7 times 0.7. 0.147. Okay, then not online, online, online. So N-O-O. So that's 0.7, 0.3, 0.3. Which is 0.063. Not online, online, not online, so N-O-N. Okay, so that's 0.7, 0.7, 0.3. I'm just going to bring that down here. That's the same as this one, so that's 0.147. Okay, then not online, not online, online, so NNO. So that's again 0.147. And then last one, all three could say not online. So N, 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 which that's going to be 0.7, 0.7, 0.7, which is going to be 0.343. Okay, so this is how you get all of your possible outcomes. But look at that. You have 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. But filling out my probability distribution here, if I come back over here, okay, you have 0. Okay, and our P of X, remember, is how many people say they are online, or, yeah, almost constantly online. Okay, so X is, if we come back over here, X denotes the number of Americans in the sample that report to be almost constantly online. So if 0 of them report to be almost constantly online, then which one is that? Let me get my... That would be NNN. So that would be this one right here. So P of 0 is going to be 0.7 times 0.7 times 0.7, or NNN, which is 0.343. Okay, the probability that one person says that, do you suppose they care about the matter or the order? They're not going to care what order it is. It's just one person says that they're online. So the probability that one person says they're online could be, let's see, this one, or this one. Okay, one of them has online. So that would be 0.147 times 3. So if you've already done the tree diagram, you can do it that way. You can add those together. If you don't do the tree diagram, because you don't have to do the tree diagram, right? You know you have 8 possible outcomes. Okay, think about the 3 ways that that could happen. Okay, one person saying they're online is 0.3, which means the other ones say they're not online, so 0.7 and 0.7. Then take that, multiply by 3. Okay, so 0.3 times 0.7 times 0.7 is 0.147 times 3, because you have 3 ways that could happen. You have online, not online, not online. You have not online, online, not online. So you think about that, okay? You do that. You're just moving the O. Those are the 3 ways that that could happen. So if you do that probability times 3, that gives you, what did we have there? 0.441. Same thing with the 2. Okay, we have the tree diagram. We can look at that. 2 people saying they're online is going to be here, here, or here. It's those middle probabilities, because the 2 on the end are the all one way or another. Okay, so it's 0.063 times 3, if you've already done the tree diagram. Okay, but you could also do this. Okay, I have my possibilities of that being 2 people saying they're online, or O, O, N, O, N, O, or N, O, O. Okay, because I'm only doing 3 drawings. Those are the 3 ways that could happen, which would be 0.3 times 0.3 times 0.7 times 3, which gives us 0.189. Or I can add 0.63 plus 0.63 plus 0.63. Or, sorry, 0.063. And then the probability that 3 people say that they are online is 000, which is this first one here, 0.027. Okay, so you can use the tree diagram to get all of those probabilities, or once you kind of go through it and you learn what the outcomes are going to be, you can go through it that way. You can do the math this way. It's really a matter of preference, and I don't think for filling out a probability table you're going to be given more than maybe 4 options. I look here. If you have more than 4 values of x, so I have one here that has 4. Yeah, if you're given more than 4 options for x, then the probabilities are given for you. The table is done. Unless it's the second part of this chapter. Okay, so you should be able to do a tree diagram with that many outcomes. Okay, now last thing here, when I'm filling out this probability distribution, I just want to check that I've done it correctly. So what you want to do is you want to add the probabilities, and they need to equal 1. So 0.343 plus 0.441 plus 0.189 plus 0.027. All right, equals 1, so we're good to go. So you want to check that. All right, next part of this is kind of going back up to the 2 types of variables. So indicate which of the following are random variables are discrete or continuous. So number of new accounts opened at a bank during a certain month would be discrete. Number of. Time taken to run a marathon, continuous. The price of a concert ticket, continuous. Number of rotten eggs in a randomly selected box, discrete. Points scored in a football game, that is discrete, yes, because we can count those. The weight of a randomly selected package, that is continuous. Okay, let's look at mean and expected value. Okay, expected value is actually the same thing as the mean. Okay, it's the long-term average expected over many, many experiments. So if I do this experiment 1,000 times, the expected value is the average of the outcomes for all of those experiments. Okay, the formula for that is the sum of x times p of x. So you do x times p of x, and then you add them. The standard deviation in a probability distribution is going to be this formula here. So you have the square root of the sum of x squared times p of x minus the mean squared. And then the variance is the standard deviation squared. So let's look at example 2.1. A hospital researcher is interested in the number of times the average post-op patient will ring the nurse during a 12-hour shift. For a random sample of 50 patients, the following information was obtained. So we have x equals the number of times the post-op patient rang a nurse. determine the expected value and standard deviation. So let's go ahead and look at that. So the expected value is, we'll do those first, and then we'll do A, B, C, and D. So weird that it doesn't copy over. Let me fix this first. So this is 5, 0.04. And we'll go back to that. Okay, so the mean is going to be the sum of x times p of x. So that means we're going to need to do that. So we're going to go x, p of x. We're going to add another column over here. And we're going to do each of those. So 0 times 0.8 is 0. 1 times 0.16 is 0.16. 2 times 0.32 should be 0.64. 3 times 0.28 there we go, 0.84. 4 times 0.12 would be 0.48. And 5 times 0.04, I think, is 0.20. Let me check. Yeah, 0.20. All right, so then the sum of this is going to be our mean. So the sum of x times p of x is, we'll add all of these together. So 0.16 plus 0.64 plus 0.84 plus 0.48 plus 0.20, 2.32. Okay, so that is our mean, which means that during a 12-hour shift, the patients rang the bell for the nurse an average of 2.32 times. Okay, with a standard deviation of, and we'll do the standard deviation. So that will be the sum of x squared times p of x. So we're going to need to do those, and then minus the mean squared. So let's go ahead and do x squared times p of x. We'll get another column here. So 0 squared is 0, so this is going to be 0. 1 squared is 1 times 0.16, so that'll be 0.16. This will be 2 squared times 0.32, so you would just go 2 squared times what was that probability? 32. So 1.28. Okay, then 3 squared times 0.28, 2.52. 4 squared times 0.12, 1.92. And then 5 squared times 0.04. 1. And then we will add all of those together to give us the sum of x squared times p of x. So let's see what we've got here. We've got 0.16 plus 1.28 plus 2.52 plus 1.92 plus 1. So 6.88. Then we're going to take that over to the formula. So we have the sum of x squared, p of x, which is 6.88, minus the mean squared, 2.32 squared, and then in the square root of that. Okay, so sum of x squared, p of x, minus the mean squared, So let's do that. What's 2.32 squared? Okay, so 6.88 minus 5.3824, and then we're going to take the square root of that. So I get 1.224. And you can put that all in at once if you'd like. I think that should be fine. Let's see. Square root of 6.88 minus 2.32 squared. Yep, works fine. So you can put it all in at once. Okay, then let's look at the questions A, B, C, and D. Okay, so P, the nurse was rang, what does that say, more than 4 times? Okay, that is the probability that x is greater than 4. Okay, well, there's only one probability that x is greater than 4. Now we're just looking back at the first table. Okay, so you're just looking at this, probability of 5. So really, that's just probability that x is 5, which is 0.04. B, the probability the nurse was rang less than 2 times. That's P, x is less than 2. Okay, so you have 2 options for that, for x being less than 2. You have 0 and 1. Okay, so that would be the probability of 0 plus the probability of 1. You would add those two together. So you have 0.08 plus 0.16, which gives you 0.24. Bless you. C, the probability that the nurse was rang at most 2 times. Okay, at most 2 times, think about what that means. The most that they were rang was twice, which means it could be 0, 1, or 2. So the notation for that is less than or equal to 2. At most. So if you have at most, it's less than or equal to. Okay, at least is greater than or equal to. So at most is less than or equal to, at least is greater than or equal to. So this one we would add the probabilities for 0, 1, and 2. Okay, so that would be 0.08, 0.16, and 0.32. So that is going to add to 0.56. Okay, then part D. The probability the nurse was rang at least 1 time. So at least is less than or equal to. So it's x is greater than or equal to 1. So you would add all of these probabilities, or you could just subtract the 0.08. That's probably easier. Instead of adding 1 through 5, you could just do 1 minus the probability of 0, which is going to be 0.92. Okay, so you have to learn your notations, be able to work that out from a table and pull the probabilities out. So at most is less than or equal to, at least is greater than or equal to. Okay, and then the other ones, more than, less than, are just like they sound. All right, let's look at a roulette wheel. Does anyone need more time with this? All right, wow, that really cut off. Let me, hmm? I am not drawing that. I might just put back in. No. All right, we're gonna go over here. Oh, we're not in chapter 3, are we? We got chapter 4. There it is. All right, let me see if I can pull a screen clipping in of this. Did I put it over that? Oh, good. Awesome. I hope when I convert this to a PDF, it doesn't mess it up, but let's see. There we go. Okay. So an American roulette wheel has 38 numbered slots, 1 to 36. Okay, so you got 1 to 36. I guess these are how the numbers are out. 0, 0, or 0 and 0, 0. All right, half of the 1 to 36 are red, half are black. Both 0 and 0, 0 are green. Okay, so before we read more into this, let's write that out. Okay, so you have red. So red. Half of the numbered slots, 1 to 36, are red. So 18, red, right? How many total on the wheel are there? 38, because you had the 36 red and black, and then you have the 2 green. So 18 out of 38 are red. 18 out of 38 are black. And 2 are green. Okay, so 38 slots on the roulette wheel. All right, just so we have that, because we're going to need those for the questions. So a ball randomly lands in one of the slots, and bets are placed on where the ball will land. A bet on red, rouge, or black, noir, has a 1-1 payout. Okay, meaning that if you bet $1, you get a dollar. So you get your dollar back, and you get $1. You bet $5, you get 5. All right. A straight bet on a single number has a 35 to 1 payout. So that's just a single slot. And a basket bet, which is 0, 0, 0, 1, 2, or 3, has a payout of 6 to 1. So if you put $1 in, you get $6. You put $2 in, you get 12, etc. Okay. So what we're doing here is expected values. So these are the means for these bets. Okay, so determine the expected value of this bet. So the expected value, remember, that is what's going to happen long term. If I play this roulette game 1,000 times and I take the average of my winnings, what is that going to be? Okay, that's what this is. So what will happen long term? What do you guys think will happen long term? Are you going to end up winning or losing? Okay, typically, if you're gambling, the house has the advantage, so typically you're going to lose long term. So the key is to know when to walk away, right? Which is hard. All right, so let's see here. So let's suppose we place a $1 bet on red. What is the expected value? So remember, the expected value is the sum of x times p of x. Okay, but we have to figure out what that is. So what we do here is we do the probability of a red. Okay, so the probability of red, and then what if we win? Okay, so if I get red and I win, I get $1 because it's a 1-1 bet. So times win would be 18 out of 38 times $1. Okay, but I also have to add the other probabilities. So I have red, black, or green. So those are the possible outcomes. So this, because it's the sum of your possible outcomes. So then we would add the probability of black. And if it gets black, then I lose. So that would be 18 out of 38. And then I'm negative $1. Because I gave them my dollar, and they took it. And green is same thing. Probability of green times lose, which is 2 out of 38. And I lose $1. Okay, so I'm adding, the probability, which is this 18 out of 38, and then win or lose. Okay, my x, my expected value. So I add these together. And really, if you look at these two here, what's that going to be? That's just going to cancel out. So it's really 2 out of, that should say 38, times negative 1. Sorry. So 18 out of 38 times 1, 18 out of 38 times negative 1, those cancel. So 2 out of 38 times negative 1, 0.053. Or negative 0.053. Okay, and if I convert that to money, that's a negative 5 cents. So if I sit there and I play the roulette wheel and I bet red every single time, and I do it 100 times, I'm going to end up walking away at the end of the 100th time losing 5 cents total. Because I'm going to win some and I'm going to lose some. Okay, that's that expected value. Win some, you lose some. On average, you're going to end up losing. But not by much, because it's a 1-1 bet. Okay. What if I bet $1 on a higher payout every time, but it's just a single number? Okay, you have, what is this? This is a straight bet. Okay, so a straight bet, so suppose a $1 is bet on 0-0. We want to determine that payout. So a straight bet on a single number is a 35-to-1 payout. Okay, so this one, we would have this, the probability of getting 0-0. What's that probability? How many 0-0s are there on this wheel? 1. 1 out of 38. If I get that, how much money do I get? $35. So I have a 1 out of 38 chance of getting $35. And then here, this would just be plus the probability that you don't get 0-0, which is a 37 out of 38 chance. But I only lose $1 if that happens. Okay, so here I would do 1 out of 38 times 35. Which is 0.921 plus 37 out of 38 times negative 1, which is 0.974. Or negative 0.974. And then if I add those two together, I get negative 0.053. It's actually the same thing as the last one. Okay, so I still come out 5 cents behind with this bet. I think that's just a coincidence on this, but I don't gamble, really. So I don't know for this. But 1 out of 38 chance, you're betting, it's got a higher expected value, so every 38 times you're going to win $35. The other 37 times you're going to lose. So you're going to end up losing $2, and then over time you're going to come out slightly below. Is it worth it? When you win, because it's the thrill of winning, right? Yeah. But then when you win, you just, okay, bye. go somewhere else. I mean, this is a game that's supposedly totally by chance, but I don't know about them maybe putting some weights on the wheel. You never know. All right, last one, a $1 basket bet. Okay, so the basket bet is 0, 0, 0, 1, 2, and 3. So probability of getting a basket. So how many ways could we win? 5 ways, yeah. So 1, 2, 3, 4, 5. So 5 out of 38. And if we win, how much do we win? $6? 6 to 1. So 5 out of 38 times $6 plus probability that you don't get a basket. Okay, so if there's 5 ways to get the basket, then there's 38 minus 5, 33 ways to not get a basket. And you are losing $1. Okay, so 5 out of 38 times 6. Is going to give us 0.789. Plus 33 out of 38 times -1. Is negative 0.868. Okay, so 0.789 minus 0.868. Negative 0.079. So I'm coming out about 8 cents for my expected value there. Question? If you're betting $1, if you're betting $2, then it would be -2. Okay, but then the payout would be 12. If it's a 6 to 1. If it was like a 6 to 5, then you would do those. So look at the ratio. For the questions that you guys are seeing, I think most of the time it is going to be $1. But here, if you look at this, so you look at the expected values, okay, then doing a basket bet is probably in the long term going to be the worst strategy here. The best strategy is either to do the red or black, or just picking a single number that has a higher payout. But doing a same thing every time. Not mixing it up, because then you're mixing the probabilities, and then you're going to really end up losing in the long run. Okay, so let me see. So let's look at this problem. So suppose you have an experiment where you draw 3 cards with replacement. So that means we're going to put the card back in every time. So every time you do the experiment, 52 cards from a standard deck. Then count the number of aces. And then we're going to construct a probability distribution for the number of aces obtained when 3 cards are randomly drawn. So why don't you guys work on this for a second? See if you can come up with these probabilities. Okay, let's think about this for the probabilities of what can happen. So you're drawing a card, right? You could either get an ace, or you could not get an ace. So what's the probability of getting an ace? 4 out of 52. Which is what? Yeah, and it says 4 decimal places, so let's stick to the 4 decimal places for this one. What is it? 0, 7, 6, 9. Okay. And then the probability of not getting an ace is what? 48 out of 52. And what's that going to be? 9, 2, 3, what? 3, 0. Okay, so those are your probabilities, ace or not ace. Now, how many outcomes of this experiment could we get? we have ace or not ace, right? So 2 possible outcomes. How many total, how many times am I drawing the card? So remember, possible outcomes to the number of experiments. So we have 8 total outcomes. Now you could do a tree diagram to list those out. So this is the number of outcomes, ace or not ace, raised to the number of experiments. So I'm drawing the card 3 times, so it's 2 to the 3rd. If I was drawing the card 4 times, 2 to the 4th, etc., etc. Okay, so 8 total outcomes. We could just list that out, so ace or not ace. So you could get no ace, no ace, no ace. You could get, let's see, no ace, ace, no ace. Or we could do the tree diagram to do them. You don't have to do the tree diagram, though. You could do no ace, and then an ace. You could have ace, no ace, no ace. You could have no ace, and ace. Let's think here. Did I already do that one? I already did that one. So no ace, ace, and ace. Let's do that. See, it's easier for me to do the tree diagram because I can visualize it, but I'm trying to do it without. Let's go ace, ace, no ace. Ace, no ace, ace. 1, 2, 3, 4, 5, 6, 7, and then ace, ace, ace. 8. Okay, so that's kind of how you could do it without the tree diagram, but you might mess up like I did. Just make sure you don't repeat any. Okay, we can get all those probabilities, but let's go ahead and fill out our table. So you have the possibility they could never get an ace. You could get 1, you could get 2, or all 3 times you could get aces. Okay, so the probability of 0 aces is this one here. No ace, no ace, no ace. Well, the probability of not getting an ace is 0.923. So I would need to multiply all of those. So I would do 0.923 times 0.923 times 0.923. Okay, so let's go ahead and do that, or 0.923 to the 3rd. So 0.78, and we're doing 4 decimal places, 0.7863. Okay, the probability of getting 1 ace. Yeah, so you could have the 1 ace, 0.0769. That's this right here, which would mean one of them are aces and the 2 are not. So then 0.923, 0.923. Okay, so we do that. And that gives us 0.6 or 0.0655. But how many ways can I get 1 ace? Let's look at that. We got here, here, or here. So we have, all of these have a probability of 0.0655. So we're going to add all of those together. Or we're going to take this whole thing and we're going to multiply by 3, because that would give us, I don't want to put a little 3 there because I don't want you to think you're raising it. So times 3. Because there's 3 ways to get 1 ace. Okay, that's NaN, NNA, ANN. Okay, so 0.0655 times 3 is 0.1965. Okay, then 2, P of 2. Okay, same thing, let's look at here. There's this one, and this one all have 2 aces. So we'll find that probability, which is going to be probability of ace, 0.0769, times the probability of ace, times the probability of not an ace. That whole thing times 3, because there's 3 ways to get 2 aces. So we'll take, oh, I did that. No, this is the last one, sorry. 0.0769 times 0.079 times 0.923. Then times 3. So 0.0164. Okay, and then the last one is just this, ace, ace, ace. So it's 0.9 or 0.0769 to the third. Uh-oh, what is that? Scientific notation? Okay, so scientific notation is this. So that's 4.55 times 10 to the negative 4. That means this decimal place has to move 10 or 4 places to the left. That's all that is. Okay? So 10 to the negative 4 would be, we'd take the 4.55. 1, 2, 3, 4. So 1, 2, 3 zeros, and then a 4. So this would round 4 decimal places to that. So 0.0005. That's probably why they wanted it to 4 instead of 3 decimal places for that problem. Okay, so if you get that on your calculator, that's scientific notation. It just means you're going to move the decimal that many ways. If it's negative, you're moving it to the left. If it's positive, you're moving it to the right. When we're doing probability, we're not going to get positive ones because then it would be bigger than 1. So it's always going to be moving to the left when you guys are doing these problems.